Hi and welcome, Pure Maths 3 students, to week 14 of our maintenance, where we continue reviewing some of the topics that we've done, just keeping them fresh in our memory, keeping those skills handy so that we're ready for the exam. Now, the first one here is an algebra question, and we've got this polynomial. We know that a and b are constants. We denote it by p of x, and we know that x plus 1 and x plus 2 are factors. Okay. Now, if they're factors, that means p minus 1 equals 0, and also p minus 2 equals 0. So those are the roots for those to be factors. For x plus 1 to be a factor, p minus 1 must be a root. So what I now do is I go about inserting minus 1 into this function here. So I get minus 4 plus a minus b minus 2 equals 0. And I could rewrite that as a equals b plus 6. So that's what a is. Now, over here I'll do the same thing with negative 2. So I get 4 times negative 2 cubed, which is negative 8. So negative 32 plus 4a minus 2b minus 2 is equal to 0. Now this gives us 4a minus 2b equals 34. We can divide everything by 2, so 2a minus b equals 17. And now we can substitute in this fellow here. So 2 into b plus 6 minus b equals 17. So we get 2b plus 12 minus b equals 17. And this leads us to b is equal to 5. And now we can substitute that in for a. So a is equal to 5 plus 6. I'm just substituting into here now. So a is equal to 11. Now when a and b have these values, we want to find the remainder when we divide by this. Okay, so what I'm going to do for this is I'm just going to set up my whoops, let's not use the highlighter every time. We're going to divide. Maybe I'll just pop it down a bit further. Our function, which we know to be 4x cubed, plus, now what did we say a was? 11. 11x squared. B was 5, I think. Minus 2. Now we plug this in. X squared into 4x cubed is just simply 4x. And that will lead us to 4x cubed. Obviously 0x squared plus 4x here. Now we can take all of those away. So we get 11x squared plus x. Now 11x squared, so we need to go plus 11 for our second one, which will give us 11x squared plus 0x plus 11. Bring down that 2. And as we take away here, we'll get 1 take away 0, so that's x, and then minus 2 minus 11, which is minus 13. So this is our remainder here. Okie dokie, moving on. Now we've got to solve, use logarithms to solve this and give the answer to 3 significant figures. So what I'm going to do first is I'm going to take a log of both sides. Like so. Then I'll use my log rule, so my next line is 5x log 2 equals 2x plus 1 log 3. And I can expand that right hand side. I'm going to bring the x's over to one side so I can factorize them, so I'll get this. There, factorize at this point. So I get 5 log 2 minus 2 log 3 equals log 3. Then the next line I divide, so I get x equals log 3 over, now 5 log 2 is the same as log 2 to the 5, which is log 32, minus 2 log 3, which is the same as log 3 squared, or 9. And I guess we could rewrite that as log 3 over log 32 over 9. And we could just, even at this point, we could just work it out on our calculator, because that's all we need to do. I'm getting 0.866. Okay. The next one is a trigonometry question. And we've got to prove this identity. Cosine 4 theta plus 4 cosine 2 theta is equal to 8 cosine to the power of 4. Okay, so, well, we're going to use a double angle rule for cosine. So this is it here. But you see that we're getting these cosines at the end. So I think we want to use this version of it, because that doesn't have any signs in it. So let's try that. Now I'm going to say that, let me see, I would write my second line as like this: cosine bracket 2 theta plus 2 theta plus, and then I'm going to use 4 times, now cosine 2 theta is this here, so I'll go 2 cosine squared theta minus 1. Okay, now actually I'm going to go back and fix this bit up, because what I could do is if I could actually use the double angle rule here and go, it's like 2 cosine squared 2 theta minus 1. Okay, see what I've done there? I've got 4 theta here, so I can use the double angle rule to get that. Now, at this point, my next line, I could take this and I could rewrite that as 2 bracket 2 cosine theta minus 1 squared minus 1. Now you'd be like, what the heck is he doing here? Okay, I'm using the double angle rule, because, let me write it over here. Cosine 2 theta, cosine squared 2 theta is like this, okay? And I know that cosine 2 theta is this here, this 2 cosine squared theta minus 1. So, oh, I should have a square in there, shouldn't I? Okay. And then I'm going to square that, because I've got cosine 2 theta squared. So that's what that squared is there. And then, of course, I've got this other bit from last time, 4 into 2 cosine squared theta minus 1. Now we can start expanding. So we get, oh, no, we can't. Oh, well, yeah, I guess let's expand that bracket there. So we'd get 4 cosine to the power of 4 theta minus 4 cosine squared theta plus 1. And then we've got that minus 1 plus, and I'll expand this last bracket here. So that would be 8 cosine squared theta minus 1. Let's expand again. So we get 8 cosine to the power of 4 theta minus 8 cosine squared theta plus 2 minus 1 plus 8 cosine squared theta minus 1. Okay, at this point, we can gather our like terms. You can see that this one and this one are going to cancel each other out. And this and this and this are going to add to... what are they going to add to? Oh, I should have had a... I just made a mistake. That should be a 4. And that should be a 4. So all up, I'm going to now get 8 cosine to the power of 4 theta minus 3. Okay. Hence, so at this point now, I've got to say, I've got to use that to solve this equation. So all I would do at this point is say 8 cosine to the power of 4 theta minus 3 equals to 2. I'm going to say 8 cosine to the power of 4 theta equals to 5. And so cosine to the 4th power is equal to 5 over 8. And cosine theta is equal to plus or minus the 4th root of 5 over 8. Now, we get two principal values when we do this. When we do the positive one, 4th root over 5 over 8, I'm getting 27.2. And when I do the negative one, I'm getting 152.8. And then we can just think about the other values that we've got. Okay, so here's 180. You've got the 152 here. You've got a 27 over here. So you need 360 minus 27 for the other one. Which, oh, never mind. Oh, don't know what's happening there. 360 minus 27, so that's 332.8. And then the other one, this one here, is we find the difference between 180 and 152, and then we add that on. So when I do that, I get 207.2. Okay. So the next one here, we've got to find the coordinate of m being 2. So we've got to differentiate this, and you can see that we're going to use the product rule. So I'm going to say u is equal to x squared, and therefore du dx is equal to 2x. I'm going to say v is equal to e to the 2 minus x, and therefore dv dx is equal to negative e to the 2 minus x. And we know the rule for the product rule. If we've got uv, then when we differentiate it, we need to get u times dv dx plus v times du dx. Okay. Now that means we're going to get negative x squared dy dx is going to be negative x squared e to the 2 minus x. So that one pairs with that one, and then the other two pair together, so it'll be 2x e to the 2 minus x. Now, at the minimum point, these must be, at a maximum point, these must be equal to 0. So we can go negative x squared e to the 2 minus x plus 2x to the e to the 2 minus x is equal to 0. We can rearrange, and so we get 2x e to the power of 2 minus x is equal to x squared e to the 2 minus x. And then we can divide. So next line, we get 1 on the right hand side, 2x e to the 2 minus x all over x squared e to the 2 minus x. And you, x. You can see that cancels that cancels that, and we're left with 2 over x equals 1, and therefore since 2, so if we've got 2 over x equals 1, therefore x equals 2. So we've done that. That's nice, lovely, lovely. The next one, we've got some parametric equations here, and we have to find the gradient of the curve at the origin. Okay, so the gradient of the origin. Okay, first of all, let's do dx dt. So dx dt is equal to 2 over t plus 2. And dy dt is equal to 3t squared plus 2. And dy dx we can think of as dy dt divided by dx dt. So it's like 3t squared plus 2 all over 2 over t plus 2, or another way of saying that is 3t squared plus 2 into t plus 2 all over 2. And we want to know the gradient of the curve at the origin. Well, that means x is equal to 0. So if x is equal to 0, what is t? So we can just rewrite this. 0 equals 2 ln into t plus 2. Well, we know that ln 1 is equal to 0. So for that to be the case, t must equal minus 1, because ln 1 is 0. So negative 1 for t would give you ln positive 1 overall, which is 0. Natural log of 1 is 0. Okay, so that is the value of t at the origin. Now we just plug it into the formula. Dy dx at the origin is going to be equal to 3 into negative 1 squared plus 2 multiplied by negative 1 plus 2 all over 2. Now what does this give us? 3 plus 2 equals times negative 1 equals positive 1 equals over 2. So I'm getting 5 over 2 for this. Okay, last page. Ooh, okay. This is a tricky one. Okay, this is a tricky one. So for this one, we're going to need to integrate by parts, and we're going to need to do it twice. And the reason we're going to need to do it twice is because you can see that we've got this x squared is our u value. You can't ever get rid of e when you're integrating or differentiating, so we're going to make u to be our x squared value. So my first step is to say u is equal to x squared, and the dv dx bit must be this then, so dv dx is equal to e to the 2 minus x. And then we can therefore say, well, what would v be in that case? Well, v would be integrating this, so it would be minus e to the 2 minus x. And obviously du dx is equal to 2x. Now we're ready for the first step in this integration by parts. Here's what we're doing. Okay, so uv, so that's x, every time, x squared, okay, this time it's not, there we go, x squared and then times v. Now v is minus e to the 2 minus x. Okay, so we've got that, but take away the integral of v. Now v is negative, so it's this one here, isn't it? Times du dx. So I'm just going to put the du dx first, 2x, and it's minus in this case, 2x into e to the 2 minus x. Okay, now you can see that we're going to actually have to repeat that process all over again. So I'm going to switch colors now. So for this bit here, I'm going to say u is my minus 2x, and therefore du dx is equal to my minus 2. My dv dx is equal to e to the 2 minus x, and therefore my v is equal to minus e to the 2 minus x. So now we're going to go minus x squared e to the 2 minus x minus, and then I'm going to put this in brackets. I'm integrating this bit here. So again, I use this uv. So negative 2x, so this is this one, times this one, okay? Well, that will give us, seriously, that will give us 2 e to the 2 minus x. And then we're subtracting the integral of v. Now v is negative 2, this one here, and then times negative 2x. So positive 2x e to the 2 minus x. Right, we're getting there. Next line. Minus x squared e to the 2 minus x minus, we've still got these jolly brackets here, 2 e to the 2 minus x minus. Now I'm going to do this bit in brackets. Maybe I'll do a different color. Maybe I'll do a really different color, like a green. There we go. Now we integrate this. What do we get? Okay, so when we integrate to x, oh, wait a second. I made a mistake. It should have been du here. Sorry, guys. Wakey. It's like, why have I still not got rid of this? Okay, so that should be e to the 2x here. E to the 2 minus x. Let's just have a quick refresh. Okay, u, v. I should have had an x here, because that's u. This is our u. 2x e to the 2 minus x. And then this second part is v, which is this bit here, times du dx. So that times the minus 2. Okay, now we're ready to go. My apologies. So when we integrate this, we're going to get negative 2 e to the 2 minus x. Okay, now we're ready to write this whole thing out. So, and I'm going to put square brackets around the whole thing because we're integrating and we've got limits 2 and 0. So we get negative x squared e to the 2 minus x minus 2 e to the 2 minus x. Now, this negative times this negative becomes positive, but then we've got this negative here. So again, it'll be negative 2 e to the 2 minus x. Right, I think we're good there, and we're doing this between limits of 0 and 2. Now, you go through this whole thing. You could, potentially if you want, you could factorize it, I guess. You could go e to the 2 minus x into negative x squared minus, that should be 2x. That should have been 2x. I forgot to change that one. Sorry guys, this is really badly done. It's 2x because I stuffed up that point before and then I forgot to change it here, so it should be 2x. Okay. X squared minus 2x minus 2. Okay. Now, when you go ahead, you're going to chuck your 2's in the first time. I'm getting minus 10. So that's my first run through. Then I put a 0 into all of that. And I'm going to get minus 2 e to the 2. And then so all up we can say, well, that's like 2 e to the 2 minus 10. So that would be my answer there. Now the next one is numerical solution of equations. Now we're referring back to question 2 on the differentiation. At the point P on the curve, the value of the parameter is p. Okay, so here we go. The value of the parameter is p. Okay, and we know that the gradient at that point is 1/2. Okay, now we worked out the gradient somewhere. Where did we work out the gradient? Here's our gradient. Okay, it was, let me just snip that down. This was our gradient. So I just pop that down here. And this, so that was dy dx. Now, we know that the gradient, when we're using p, is 1/2. So we go 1/2 is equal to, and we're going to go 3p squared plus 2 into p plus 2 all over 2. Now, our next line, we times both sides by 2, so we get 1 equals 3p squared plus 2 into p plus 2. Now, we're trying to show that p is equal to this. So probably what I would do at this point in time is I'm going to divide both sides by the 3p squared plus 2. So I would get 1 over 3p squared plus 2 equals p plus 2. And that leads us to what we're trying to prove. So p is equal to 1 over 3p squared plus 2 take away 2. So that wasn't so bad. Now, by first using the iterative formula based on that equation, determine the coordinates of point P. Okay, so well, we're not really given any indication of whereabouts that P value is, but I'm just going to start off with x equals 1 and see where we get to with this. So, P1 equals 1. I typed that into my calculator, and now 1 and press equals, and 1 is my answer. And then I'm just going to go, all right then, 1 over 3p squared plus 2 minus 2. And then I'll get my iterative formula happening. So when I do this, my P2 is going to be negative 1.8. My P3 is going to be negative 1. Now I'm giving the iterations to 5 dp, so make sure you do that if you've got 5 dp. I do in this next one. P4, because you don't want to lose marks for something as easy as this, 1.92306. P5, negative 1.92363. The P6, negative 1.92367. P7 equals negative 1.92367. One more for good luck. P8, negative 1.92367. And therefore we can give our result at this point to 2 dp. So P equals 1.92, negative 1.92. Now, that's not it, because we want to. That's not where we're totally needing to get to. We need to find the values of each coordinate of P. So we want the x and y coordinates. So all we need to do now is we go back to what x is. We were told earlier in the question that x is equal to, this is in the differentiation part, ln 2ln p plus 2, or x plus 2. T plus 2, but remember t is equal to p in this, or p is equal to t in this. So I'm chucking in a p for t. And when I do that, I'm getting negative 5.15. And we were told that y is equal to t cubed plus 2t plus 3. But we're using, oh, I don't know what's happened there. We're using the value of p for t in here. So chuck in your p value of negative 1.92, and when you do that you get negative 7.97 for your y value. So that's your coordinate, the x and y coordinates of P, two decimal places. Wow, that was long. I hope this has been helpful to you. If you do have any questions, oh goodness me, or you've got any corrections to make, because I'm pretty tired and I may well have made some mistakes here, just let me know. And we'll take a look at it. All right, God bless, team.